Hi everyone, this video is made for LE260 project, and today I'm gonna talk about Transformer. But before we begin, I would like to announce that I have divided our topic into 7 main parts, begin from general understanding of Transformer, ideal practical transformers, equivalent circuit and parameters, impedance transfers, polarity, auto transformers, voltage regulations, efficiency, and 3-phase transformers at the end. Let's begin with what is transformer and its importance. A transformer is defined as a passive electrical device that transfers electrical energy from one circuit to another through the process of electromagnetic induction from Faraday's laws. It is most commonly used to increase or decrease voltage levels between circuits. For characteristics of a transformer, the frequencies of input and output power is the same. All transformers make use of electromagnetic induction laws. No moving parts are required to transfer energy, so there are no frictions or voltage loss as with other electrical devices. The losses that do occur in transformers are smaller than those in other electrical devices and include copper loss and core loss. So, how that is important to our life? Take a look at this figure. The power stations will use a step-up transformer to increase the voltage and reduce the currents, as this will reduce the loss for the long transmission cables. Then, once it reaches a city, this will need to be reduced to make itself and usable for residents. So, there will be a step-down transformer at the end. Otherwise, if we send the electricity direct from power station, it would have caused a massive explosion. In general, we normally use electrical transformer to raising or lowering the voltage level in the circuit of an AC, preventing the passage of DC from one circuit to another, isolating two electrical circuits, stepping up the voltage level at the sites of power generations before the transmissions and distributions can take place. Commonly, applications of electrical transformer including pumping stations, railway, industries, commercial establishments, windmills, and power generation units. Part 2. Ideal transformers versus practical transformers. Ideal transformer is nothing but a transformer which has 100% efficiency. In this case, there are two purely inductive coils, so this is no iron loss, no copper loss. Also, there is no ohmic resistance drop and no leakage drop. But in real life, a practical transformer was made which differs from the ideal transformer in many aspects. The real transformer has iron loss, winding resistance, and magnetic leakage. Since the iron core is subjected to the alternating flux, there occur eddy currents and hysteresis loss. These two losses together cause iron loss, which depend on supply frequencies, the maximum flux density in core volume of the core, and so on. Winding resistance. When current flows through the windings, there will be power loss as well as loss in the voltage due to the IR drop. This will affect the power factor, and E1 will be less than V1 while V2 will be less than E2. Leakage reactance. When we provide supply to primary of transformer, an EMF is produced in the primary coils since electrical coils are inductive. So, it induces magnetic flux, but what happens to the flux lines, which are small circular at each side? Their circles are not large enough to pass through the core, so it wastes off magnetic field and hence energy. So it needs to be considered as some sort of leakage in flux transformer from primary to secondary, although latent flux in transformer is quite small compared to the main flux, yet it cannot be ignored. By analyzing this equivalent circuit, the reviewer voltage, current, and impedance can be evaluated, and the actual quantities can be determined from them if the turn ratio is known. What happened here? Then we will drop across it because some part of I1 is I0, which is very less. So we can say that I1 is approximately equal to I2 dash, so we can recall it as an approximately equivalent circuit of transformers. In order for a model to be useful, there must be a way to determine the value of the model parameters. Two simple tests are applied to determine the values for the parameters for the transformer equivalent circuit. These two are the short circuit and open circuit. The connections diagram of short circuit test or impedance test on transformer is as shown in figure. The low voltage side of transformer is short circuits, and wattmeter, voltmeter, and ammeter are connected to high voltage side. The ammeter reading gives primary equivalent of full load current. The voltage applied for full load current is very small as compared to rate voltage. Hence, core loss can be neglected. Thus, the voltmeter reading can be taken as copper loss in transformer. Copper loss here equal to I square R, where I is the equivalent resistance of transformer. The impedance equal to V over I if C is equivalent impedance of transformer. Therefore, equivalent reactance of transformer can be calculated from impedance square equal to R square plus X squared. Hence, it is seen that the short circuit test gives copper loss of transformer an approximate equivalent resistance and reactance of the transformers. Open circuit test or no load test on a transformer is performed to determine no load loss and no load current. The circuit diagram for open circuit test is shown in the figure. We open high voltage side of the circuit, and for low voltage side, winding is connected to its normal supply along with wattmeter, ammeter, and voltmeter. The primary current is the exciting currents, and the loss measured by the voltmeter are essentially the core loss. The equivalent circuit shows that the parameter R and X can be determined from the voltmeter, ammeter, and voltmeter readings of transformer and short parameter of the equivalent circuits. Hence, it is seen that open circuit tests give core loss. Moving to impedance transfer part, impedance transfer is very useful. It eliminates a copper circuit in an electrical circuit and thereby simplifies the circuit. From equations of impedance, C2 equal to V2 over I2. By referring to a turn ratio equations, we finally can indicate the relations between C1 and C2 that C1 equal to C2 over A squared. For example, here we assume that input power equal to output power, so we can write that I squared R1 equal to I squared R2. So we decide to move the I together, and here we got A squared R1 equal to R2. If we take resistor from secondary to primary side, then it will be called R2 dash. We call this procedure as resistance transfer with reference to primary. So we're gonna have R2 dash equal to R1 over A squared. However, for the opposite, if we transfer from primary to secondary, we will have R1 dash equal to A squared multiplied by R2. Next, polarity. Transformer polarity depends on which directions the coils are wound around the coil, counterclockwise or clockwise directions. There are additive and subtractive polarities of transformer. In here, we're gonna take a looking at determining them and why do we care about them. One thing that have to keep in mind is that odd numbers on terminals are going to indicate negative numbers, and even numbers on the terminal are going to indicate positive numbers. The easiest way to identify which one is additive and subtractive polarity transformers is to look at H1 and X1 terminal. In additive polarity transformers, we will notice that they are diagonally across from each other, whereas when we look at the subtractive polarity transformer, we will notice that H1 and X1 are directly across from each other. In this example, I'm gonna use a step-down transformer from 120 to 12 volts. Start by jump a wire across each terminal and apply 120 volts to primary coil. So in this case, additive transformer, if we go on clockwise directions, we're gonna get a negative 120 volt plus a negative 12 volt. So we will end up with negative 132 volt, but it is still a potential of a 122 volt. So we can see that we're going to get a more voltage than start voltage. As we said, all numbers on terminal are going to indicate negative numbers, and even numbers are going to indicate a positive number. So again, in this case, we're gonna have negative 120 volt plus 12 volts, so we will have less voltage compared to the initial value. We should see it around 108 volt. So additive polarity, when we connect it up correctly, we should see a higher than applied voltage. In contrast, when we connect it up for subtractive polarity, we should see that secondary coil subtract from the primary coil, so we will get less voltage output. Talking about auto transformer is a transformer with only one winding wound on a laminate core. An auto transformer is similar to a two-winding transformer, but differ in the way the primary and the secondary winding are interrelated. The primary winding AB, from which a tapping at C is taken, such that CB acts as a secondary winding. The supply voltage is applied across AB and the load is connected across CB. The tapping may be fixed or variable when an AC voltage V is applied across AB. An alternating flux is set up in the core, and as a result, an EMF is induced in the winding AB. A part of this induced EMF is taken in the secondary circuit, neglecting no load current, leakage reactance, and loss. When we write ampere turn by upper half and lower half for ampere turn balance, we're gonna get I1 over I2 equal to 1 over 8. Let's see the advantages of auto transformer: lower leakage reactance, lower loss, lower exciting current, increasing kVA rating, and better regulations. For the disadvantage, the direct connections between the primary and secondary sides. If an auto transformer is used to supply low voltage from a high voltage and there is a break in the secondary winding, the full primary voltage comes across the second terminal, which is dangerous to the operator and the equipment. So, the auto transformer should not be used for interconnecting a high voltage and low voltage systems. So, what is voltage regulations? For transformer, voltage regulations is used to identify this characteristic of voltage change in a transformer with loading. It is defined as the change in magnitude of the secondary voltage as the load current changes from the no-load to the load conditions. The voltage regulations depend on the power factor of the load. This can be appreciated from the phasor diagram of the voltages. The locus of V1 is a circle of radius IC. The magnitude of V1 will be maximum if the phasor IC is in phase with E load. Therefore, the maximum voltage regulations occur if the power factor angle of the load is in the same as the transformer equivalent impedance angle, and the load power factor is lagging. Just like any other electrical machines, efficiency of a transformer can be defined as efficiency equal to output power over input power, or Pout over Pout plus loss. In general, transformers are the most highly efficient electrical devices. Most of the transformers have full load efficiency between 95% to 98%. Maximum efficiencies occur when the variable loss equals to the constant loss, since the copper loss is load dependent. Hence, it is a variable loss quantity and the core loss is taken to be the constant quantity. From these equations, we assume that the core loss equal to the copper loss to meet with the conditions of maximum efficiency. This shows that we can obtain maximum efficiency at a full load by proper selections of constant and variable loss. We can see from the figure that the maximum efficiency occurs at unity power factor, and the maximum efficiency occurs at same loading irrespective of power factor of the load. For all-day efficiency, when secondaries of transformer are not supplying any load, then only core loss of transformer are considerable and copper loss are absent. Mark that copper loss are considerable only when the transformers are loaded. Thus, for such transformers, copper loss are relatively less important. The performance of such transformers is compared on the basis of energy consumption in one day, so the all-day efficiency could be calculated by output power over input power for 24 hours. Last but not least, three-phase transformer is used to generate and transmit huge amounts of electrical energy. It is required to step up and step down voltage in the various stages of power transmissions. A three-phase transformer can be built in two ways. First, bank of three single-phase transformers, and three-phase transformer on a common magnetic structure. Bank of three single-phase transformers. A set of three single-phase transformers are connected to form a three-phase transformer. Each primary and secondary winding may be connected in either Y or delta configurations, so it generates four possible types of connections. First, Y and delta. This connection is commonly used to step down a high voltage to lower voltage. Second, delta and Y. This connection is commonly used to step up voltage, delta and delta. This connection has the advantage that one transformer can be removed for repair and remaining two can continue operating. Y and Y. This connection is rarely used because of problems with the exciting currents and induced voltage. For three-phase transformer on a common magnetic core, a three-phase transformer can be constructed by having three primary and three secondary windings on a common magnetic core. Although this structure is not convenient to build and has some imbalance which is not that significant, it provides transformer way less coreless and requires less space than a three-phase transformer bank of the same rating. However, the disadvantage is that if one phase breaks down, the whole transformer must be removed for repair. By far, the benefits of three-phase over single-phase transformer is that it is less cost, less weight, requires less space, delivers more power, higher efficiencies, and easy to transportations and installations. That's the end of the transformer. Thank you for your attention.